Hello, I'm Neeraj. Today I will explain the concept of Dora, a weight-decomposed low-rank adaptation techniques authored by these authors. What happens when we train the large language models by using publicly available resources? We store all the learned relations through some weight matrices. And in the fine-tuning process, we just play with those weight matrices. So we already discussed that why we need fine tuning. Actually what happens, all those large language models are trained on publicly available resources, and when we require to use it for our personal task, our specific functions, domain adaptations, task adaptations, and a lot of such kind of activities, then we need some fine tuning process. So all such techniques like low rank adaptations, quantized low rank adaptations, Dora, all such are actually fine tuning techniques. So here in this paper, in this tutorial, we will try to understand that how this current method Dora is different from the previous methods like Dora. So just we will take low rank adaptations techniques, because Dora is actually developed on the top of LoRa. So the authors of this paper, D0RA, actually pointed some issues with old low rank adaptation techniques. Actually what happens in the low rank adaptation techniques, they take the pre-trained weight matrices and randomly initialize a lower rank matrices, and instead of fine-tuning the entire matrices, they work on those lower rank matrices to fine-tune the complete pre-trained model. So in that case, the authors claim that LoRa fails to consider the full representativeness of the weight matrices, because it just considers like low rank matrices. And they also assume that if we fail to properly identify the rank of the matrices, means a optimal rank of the matrices, then in that case the model low rank adaptation techniques, when we go through backpropagations, then it may result in overfitting also. So these are some issues. So the current method Dora actually tries to solve this. So how it solves? So here in this figure it is clear that it takes the pre-trained weight matrices, and then instead of just separating the low rank, randomly initializing the low rank matrices, it decomposes this into magnitude and directions. So we will understand this process through this example. So suppose instead of big matrices, we have a small 3 by 3 matrices. So how to decompose into magnitude and directions? So to compute the magnitude, we just take the Frobenius norm of the matrices, which represents the overall scale of the weights. So Frobenius norms computations is very easy. Just to take the sum of squares and then take the square roots. So in this case, if the Frobenius norm of this matrices will be equal to 14.07. And the second part is take the direction. So what is the direction? So direction is the normalize the matrices to get the directions. Means we just normalize the matrices. So we will normalize these matrices by using this magnitude and get the directions. So to normalize, we will divide it with this magnitude, and this is our direction matrices. So this is the first part of Dora algorithm. Now the next part of the Dora algorithm is very much similar to the low rank adaptation techniques. It will take these direction matrices and apply the fine tuning process that is applied in the LoRa. So we will see how it works. So we will take that initial matrices that we calculated here and apply the fine tuning with LoRa. Means only direction part we will apply the low rank adaptation techniques. So here, just for simplicity, I will explain like how it is working. This phase is working, like how we will fine tune this. So we will take this direction matrices, select some rank. Suppose we selected just r equal to 1. Just for simplicity, you can take something better. So we will randomly initialize the matrices A and B, low rank matrices. So first matrices will be like, suppose this is a 3, number of rows and number of columns are 3 by 3 matrices. So we will take 3 by 3 into 1 matrices, because R is equal to 1, and 1 into 3 matrices. This is B. So we will randomly initialize these matrices A and B. So why we are taking the random value? You can ask questions, because if we take such kind of random values, then in proper learning process, through in the backpropagation process, it will learn the appropriate weight, and it will reduce the chances of overfitting. That's why we are taking the random weight here. So now the next part is to compute the low rank updates. So this update is just like a multiplication. So we will multiply this and this, and we will get this matrices, 3 by 3 matrices. Now the next part is to update the direction matrices. To how to update? We will add this delta V in this V. So here you can see that we have added, and this is our updated direction matrices. And after that we will normalize the updated direction matrices. I am just leaving it as it is, but we can normalize it by, suppose, by taking the highest value or something. So I am not normalizing it, just for simplicity in the calculations. Now the next step of the Dora algorithm is to, after this part, this is the second part we completed, this is the third part. So third part is merge the magnitude and direction, and this is the merged part. So how to merge the magnitude and directions? So magnitude that we had calculated, we are assuming that means magnitude may also change. For example, here we have calculated during the learning process, but we are assuming that it is 14.07, and the normalized, suppose we are considering that this is our normalized updated direction matrices. So we will multiply the magnitude with updated direction matrices, and this is our process. So we will use this process and apply the back propagations. So one questions may be like, why we are using Frobenius norm here to calculate this. So another benefit of using Frobenius norm is like it is differentiable. So when we run the back propagation and update all the random values, so that we can get the finally learned fine-tuned values here, it will be very easy for us. Means it will support the back propagation. So this is the entire process, and so I think now it is easy for everyone to understand. Now we will go through the code, like how to write the code. Actually, writing the code is very much simple, and similar to previous code that I had submitted for low rank adaptation techniques. So here you have to install the transformers, and you have to install the PFT also. I have used the same library. So LoRa config and get PFT model, and then now same like previous tutorials, I have used the questions answer data sets. So we have some questions, we have some context and some answers. So we will take the same data set again. We will tokenize by using auto tokenizers from Llama 3. Actually, for entire thing, we have used the Llama 3 model from the Hugging Face. So in the previous tutorials, I have also explained that how to download the Llama 3 models for offline purpose from Hugging Face and use it. So you can watch that part. And I have stored it here. So we will call the tokenizer and model both, which is stored in this folder. And then here it is important, because what happens several times, the length of the questions may be different. So in that case we have to apply some padding. And then this is the main part. And after that, if you have seen the previous coding examples of low rank adaptations means fine tuning using low rank adaptations, then I think this part will be very easy. I have just made this change, use Dora equal to true in the entire code, and this is the sufficient to run the Dora based system for fine tuning and applying such kind of question answering facilities in the Llama 3 model. And another thing is like target module. So we have used the query and value projections layers to update that. You can go through the Hugging Face website to select your layers from which layers you want to fine tune your model. For just a simplicity, I have used the query projections and value projections models and try to keep it very simple. And after that, with all those configurations, we will take the PFT model and then generate the prompt for data. And then all those things are very much simple. So we will map the data set and then generate the prompt data point. And then we will tokenize the prompt also, tokenize the entire data set, and then we will train it. So training, it is very much simple, like number of batch size equal to 1, gradient accumulation step is 8, number of train epochs just 3, because I am using this entire training in a personalized laptop, CPU laptop, not GPU laptop. So just 3, and learning rate I intentionally kept low because I'm using this CPU based system. But you can set it according to your choice or based on the best you can apply some grid search or you can apply some other process to get the best hyperparameters and parameters. So now we will create the trainer. So we will call the trainer and then train data set like tokenized data set, and then take the training arguments and then take the transformer data collections for language modeling tokenizer. And so here you can see how we saved our trained models. So here we have saved our trained models. So once you save this, write this model, run this model, and then after that you can test it. So testing process is almost same like we use for low rank adaptation techniques. Now to run the test part is very much simple. Same like I have written the code for low rank adaptation techniques, like just to go through that explanations, it will be easy to understand. So we define the tokenizer model, we take the device equal to CPU, then we will use the model dot to device, and then we will apply the padding. So in the case of test, I have used the US token because I want that system should understand the end of the sentence also, and then padding, or do the padding also. And then for evaluation data, we have just took the questions and then context, and to test it we had provided answers also. So after that we will generate the prompt and then test the models. And when you run this code after training or after fine tuning, you will get the correct answers. If you want to see the differences, like how after fine tuning your model performs better than the existing model for your personalized task, then I will prefer you to take the bigger data set instead of such kind of data set. Now another thing is like I have designed like questions, context, and answers. So similar to the question answering, you can take another data set also. For example, I have taken in the previous fine tuning examples, I have taken sentiment classification data set. So you can take that data set also to train your system. So for any kind, even you can define your own task to train or to fine tune your large language models.